Hi, we are continuing our discussion with array structures or subsystems, and today we're going to focus on the ROM, read-only memories, and basically what we have said last time in the introduction of the previous lecture, that read-only memory they retain the data even if we power off the device. Typically, ROM built using one transistor, okay, and this is important because it gives it the perfect sizing and compactness, etc. And the preferred structure is the NOR array, although NAND array is used in Flash, so we will explain the two of them. We can implement those NORs or NANDs using dynamic gates or pseudo random, pseudo NMOS gates. Both are used in the VLSI designs. The thing that we need to revise before we get into the details of the ROM. The ROM typically is an implementation of adding minterms. We add the minterms of a function, or we multiply the maxterms of a function. Both are valid ROM implementation. Excuse me. Both are valid ROM implementations. So let's take for example this function a or bc, and if we expand this into its midterm, we need you can use the K-map, so you can see that the midterms are those. Okay, so you can see that this function in terms of midterm is midterm 3, and midterm 4, and midterm 5, and midterm 6, and midterm 7. Now, to implement such a function, implementing midterms is to the core of ROM design, because they basically implement the midterms. We can do this very simply by feeding those inputs, which are the variables of the function ABC, into a decoder, in this case 3 by 8, and then the output of this decoder are the midterms, so we can pull the third, fourth, fifth, sixth, and seventh output into an OR structure, okay, which is right here, into an OR structure. Of course, we know that in CMOS we need to implement the OR as NOR plus an inverter. Okay, so this is an implementation where we use the OR or the NOR implementation. Now, for that, what I had to do is I used a decoder and an OR followed by an inverter, and obviously what I have to add are the minterms. Okay, now I could use mirror implementation for the f function by using the max terms. If I multiply m0, m1, and m2 for the same function, these are the max terms, and I get the same function. So for instance, to get this implementation, what I need is the same decoder, same variables fed into it, 3 by 8 decoder, same variables. However, the outputs are inverted so that I can get max terms. Okay, and now what I need is I need to AND max term 0 with max term 1 with max term 2, and to implement an AND, typically we have a NAND gate followed by an inverter. Both implementation, the NAND and the NOR, are used to implement the ROM implementation. Okay, so let's revise now what we said. The ROM implementation typically implements function as sum of minterms or multiplication or multiply of or product of max terms, and for the implementation of sum of minterms, we use the NOR implementation with a decoder which has a true output. And for the one product of max terms, we use a inverted output decoder and we use a NAND gate to implement the product. Okay, so this is kind of a quick review of implementing functions using minterms or maxterms. Now, um, so for a RAM implementation, if suppose I need to implement this memory, and I think I'm gonna get now to the whiteboard, and in the whiteboard I have basically this is the whiteboard here. Let's see if I can expand this a little bit. Okay, now here is the problem or what I need to do. I need to implement a memory, okay, a read-only memory, a ROM memory. And in this memory, I have how many words? I have one, whoops. I have one word, two words, three, four words. Now, to address those words, I need two address bits. So I assume that I have the address bits are A1 and A0. Okay, so for word 0, I am assuming that if I have A1 here and A0, that the value of A1 and A0 will be 0, 0. For word 1, it will be 0, 1. For word 2, it will be 1, 0. For word 3, it will be 1, 1, the value of the address bits. Now, the words have 6 bits, so I have here, if I can separate them, so this is 1 bit, this is the second bit, this is the third bit, and this is the fourth bit, and this is the fifth bit and sixth bit. And you can see that this one here is what he calls Y5, okay, and this bit is Y4, and this bit is Y3, and this bit is Y2, and this bit is Y1, and this bit is Y0. So those Ys are the individual bits of the word. So the width of the word is 6 bits. Now, I want to implement this memory. Now, clearly, what I could do is if every one of those bits is a function by itself. So I can say I can implement Y5 as follows. I can take the A1 and A0 feed it into a decoder, okay, all right, a decoder, and it is a 2 by 4 decoder, and I'll get the 4 output 0, 1, 2, 3. These represent the words or the minterms. And notice now this function that is Y5 here, notice it is 1 during word 2 and 1 for word 3, but it is 0 for the word 0 and word 1. So I can see that Y5 is really a summation of midterm 2 plus midterm 3, right? Okay, and therefore I can see that it is, I can, sorry, I can take the output midterm 2, midterm 3, send it to a NOR gate inverter to make it a, and that is Y5. Similarly, I can do the same thing for Y4, Y3, Y2, Y1, and Y0. And let's take, for example, Y0. Y0, the same decoder, we need to decode. Okay, so A1 and A2 and A0, sorry, goes to a 2 by 4 decoder. Okay, and I have here the output. Let's see, I have here the output 0, 1, 2, 3. Clearly for Y0, okay, for Y0, clearly the output here is at okay, so for Y0 I have I have to sum minterm 0 plus minterm 1 plus minterm 2. Okay, so now what do I need? I pull it into a NOR gate and an inverter, and that is Y0. Okay, so clearly I can implement those y's that they represent the individual bits of the word in my RAM memory. Every y of those is a function that can be implemented by adding the minterms, and the minterms are the product of this decoder. So let's go to his solution and see that what he has done. He took A1 and A0, fed it into 2 by 4 decoder. Okay, and then now he is the output of this decoder are these minterm 0, 1, 2, and 3. And then he did exactly what we have done, but now he's doing this stuff in the transistor level. So for example, look at Y5 here. Okay, look at Y5, what he has done in the Y5. The Y5 is implemented a NOR gate, okay, and basically the NOR gate from minterm 2 and minterm 3. So let's take this into the transistor level of what he has done here. What he has done is they implemented the NOR gate as such. Okay, so this is minterm. This is the output minterm 3. Let's see. This is minterm 2, minterm 3. Okay, all right, and this is ground here. This is ground, and this is a pseudo NMOS OR gate, and this is the output here, inverter, and then you get Y5. This is exactly what he has done here. This is exactly what he has done here. Okay. All right. And similarly, the other ones, you can implement the NOR gate for Y4, Y3, Y2, Y1, Y0. Okay. And notice that these minterms and words, they mean the same. So word 0 is actually minterm 0. Word 1, minterm 1. Word 2 is minterm 2. Word 3 is minterm 3. Okay. Now you can see there is a one-to-one correspondence between the presence of a transistor and the zero. So you can look at this memory here. Whenever we have a zero, right, for minterm 0, there is an absence here of a transistor. And I have here a 0, absence here of a transistor for Y5. But then I have a 1 here, there's a presence of a transistor. A 1 here, a presence of a transistor. Look at Y0 here. Y0, you have a 1 here. So you have a transistor here for word 0. You have a 1 here at word 1. So you have a transistor here connected to word 1. You have a 1 here at word 2. So you have a transistor here connected to word 2. But you have a 0 here. You have no transistor here connected to word 3. So the presence of a 1, it means you have a transistor. The absence of a 1, the presence of a 0 corresponds to the absence of a transistor. We can simplify this by using a stick diagram. And the stick diagram basically here, I can represent this as these are word 0, word 1, word 2, and word 3. And this one here, Y5, Y4, Y3, Y2, Y1, Y0. And these dots represents ones or transistors. And the absence represents what? A 0 or the absence of a transistor. So the presence of a transistor means a 1, and the absence of a transistor corresponds to a 0 for in the word of the memory. Okay, all right. So this memory, I have implemented now a memory where how many words I have? 4 words. Okay, and how many bits I have for each word? 6 bits. Okay, so this is 4 word by 6 pseudo NMOS ROM read-only memory. We'll go back to the slides. Okay, and this is basically what we have implemented. And now, so basically in general, mask ROM, what they do, they can be configured as, so let's see if you can get a highlighter here. Okay. Mask ROM basically they can be configured. Configured means what? It means that I can store a 0 or a 1 by what? By the presence or absence of a transistor. I can, as we have seen. Now we can go further, or contact. Contact, yeah, yeah. You see, the presence and the absence of a transistor, it was in the old technology. It was used for some time. Good, it reduces capacitance as move a transistor, but unfortunately, I have to design the entire ROM in the factory. I cannot program it in the field. So, or I cannot. It has to be completed at once. But people got a little bit more sophisticated, and then it says, okay, what about if we program contact? And for programming contact, that was useful when we program with metal contacts, in the sense that you complete the manufacturing of the wafer all the way to the metal layer, then you put it in the shelf, then the customer comes in and says, do for me this function. I need this function. And said, okay, we will implement the metal contacts in such a way that we implement your function. Okay, so this is one method. This is two methods, right? Or based on the threshold implant, and this is the modern way of doing things, where what we do is that we basically modify the threshold of the gates to represent or zeros. Okay, so that's basically the model. Now, programming a ROM, that means that you can basically take a silicon and write into it, and programming meaning to write into it. There are multiple types. There is the programmable ROMs, there is the erasable programmable ROMs, EPROMs, and the electrically erasable programming ROMs, which is EEROM, PROMs, and then there are flash memories. Okay, and all of them it requires some enhancement to the standard process of CMOS, like using fuses or using floating gate with which we can modify the threshold on it. Okay. Now, for programmable ROMs, this is can be populated with transistors. Okay, and then we add in series of every transistor a fuse. That is for the PROM, the PROMs. And this fuse, what we could do, we can selectively fuse up some of those fuses or burn them so that we isolate some of the transistor, meaning remove transistors to implement zeros. Okay, those transistors that we want them still there, they will implement ones. Okay, so that's the programming part of it. Unfortunately, such a technology allows you for one-time programming. You couldn't even reprogram. Now, then the industry improved later on and allowed me to reprogram the memory by implementing the erase operation. Okay, so this is where you have the EPROM and EEPROM and the flash. Okay, and before that, we need to understand the concept of the floating gate, which enabled the erasability concept. And the concept of this depends on what we call floating gate. Now, before we get into the explaining of the mechanics of the floating gate, the floating gate really depends on programming the VT of the device. I can program the VT of the device to be so high, for example, above VDD, which I can consider this device deemed to be always off all the time. Well, if you have a device with a VT equals VDD, then there is no voltage on the gate that can turn it on, because the maximum voltage I have on the gate will be VDD. If the threshold of the gate is VDD, then this device is always off. This is typically used for NOR implementation. Okay, now if I want to remove a device from so let's say, for example, if I have a NOR gate So suppose I have this NOR gate, two devices, right? And this is, let's say for instance, this is minterm 0 and minterm 1. Suppose my function needs only minterm 0 and I don't need minterm out. So how to remove this device? Very simple. Make this device VT above VDD. So it is as if this device is always off because you have made its VT above. So this device becomes always off. But you keep this device, under normal operation. This device, you keep it under normal operation. So under normal operation, because if you have VGS less than VT, which is this minterm, then this guy is off, the transistor is off, and if the voltage in M0 is greater than VT, then you turn on this device. So this one becomes normal or stays as normal operation. But this device here, which connected to M1, we completely turned it off until I reprogram it again. Okay. Now, so this one type of programming. Another type of programming is we use it in NAND operation. So the previous one, it is used in what type of gates? In NOR gates. The other type, it is in the NAND gates. And in this, basically what I do is that I have a series of, sorry. Let's see if we go back to here and just remove that. Okay. Now, if I have a series of transistors, okay, let's say for example this one here. So suppose for example I need, so this is connected to M0 bar, and this is to sorry, let's not do that. Let's do this the right way. This is connected to max term 0 and this is connected to max term 1. And let's suppose I need to keep this, but I need to remove this. I need to remove so the output here is just M1, for instance, connected to M1. Okay, of course after the inverter here. So it would be just max term 1. So how to remove the transistor connected to max term M0 here? How to remove this guy? Well, very simple. What do? I program the VT for this device. I program the VT for this device and make the VT negative. If I make the VT for this device negative, then this device becomes what? Always on. And if this device becomes always on, it is irrelevant of the value of M0, meaning it acts as a short circuit, meaning it is as if the transistor doesn't exist. Okay, so making this a negative volt, a negative VT makes it always on. It is not existent. And in what structure I used it? For the NAND structure. We say that the ROM can be implemented NOR structure or NAND structure. Now, what about this transistor here? Well, this transistor is normal operation. It depends on the voltage of the M1. If it is less than VGS or less than the VT. Okay, so I can implement if VGS, if the voltage is less than VT, then I can implement a 0. If the VGS greater than VT on M1, then this transistor is not accessed. When I turn on or when I place a 0 here, it means it acts or places a 0 on this transistor, and it represents a 0. Okay, so notice here the always off versus always on. How this represents a 1 and how this represents programs a 0. Okay, notice the similarity here. Okay, now with that said, let's introduce the concept of the floating gate. What the floating gate is, when we studied CMOS process, we know that on top of the silicon we have this SiO2 layer, silicon dioxide. On top of it there is a polysilicon. Okay, so we stopped here. We stopped all the way here. Now then what they did, they added another SiO2, another layer, and another gate here. Now what happened is that this gate here becomes floating. Okay, so the fact that this gate is floating, this intermediate gate is floating, makes it between two SiO2 layers. So what do I do then? What's the concept here? Well, the concept, what they do is that they place a large voltage here on the gate. Okay, and what happened, they pull these electrons all the way into the intermediate gate. This process, it jumps through the thin oxide. It is called a Fowler Nordheim tunneling. So I pull electrons here. When I pull electrons and I trap them in this layer, effectively the volt, the VT for this device increases, because to turn on the device and establish a channel, I have first to compensate for these electrons first, and then I can establish the channel, meaning my VT will increase. So if I can control how many electrons that are being pulled in this floating gate, I can make this VT higher and higher. Now, if I make VT reaches all the way to VDD, I have inhibited or turned off this device completely, as we have seen or explained in the previous slide when we said in the NOR structure, you make the transistor that you don't want, you make it with a VT greater than VD. So this is one way of how you change. So the idea, you manipulate the VT by introducing these electrons. Now, once I don't need them, what do? I reverse the process. I apply the positive voltage on the substrate, and then I pull out these electrons in a reverse process out of the floating gate to return the gate to its normal VT and normal operation. So by injecting electrons into this intermediate floating gate and removing it, I can increase and return the VT to its normal operation, and thereby I can program this device from being always off to the normal operation. Okay, and now we continue. This is the concept basically of how I can do erasable programmable ROMs. By using the concept of the floating gate and programming the VT of these gates. Now, of course, EEPROMs and Flash are cousins. They are related, except that Flash is the compact implementation of EEPROM, and it's smaller, and that's why Flash took off as the in consumer electronics, because it allows me to implement read-only memory with cheap, compact, economical size. Okay, now let's discuss the NAND gate, which is then of read-only memory, which is the representative of all these memories that are out there in the flash design specifically. So let's see if I can go to oops. Okay, so okay, oops, sorry. Yeah. Okay, so this is in this side here. Oops, again, this is not doing. Okay. In this side here, what I have is what I explained earlier, which is the NOR implementation. And in this side here, I'm going to explain the NAND implementation. And notice that what we have here is that in the NAND implementation, look at the differences here. The differences, the very first difference, look at the decoder. True outputs, inverted outputs. I use here the min terms. I use here the max terms. Okay, so this, look at the similarities, and also you can see here, like for example here, if you see here in the Wi-Fi, and the Wi-Fi equals what? Equal min term 2 plus min term 3. So this is 0, 1, 2, 3. But here for the Wi-Fi, since I implemented with the AND implementation, y5 equals minterm 0 multiplied by minterm 1. Okay. Okay, so it's the same y5. Logically it's the same, but this is using min terms, this is using max terms. Using min terms we use NOR gate, using maximum we use NAND gate. So here is the NAND gate. Let me take y5 here and show you how this is. Basically you have two transistors here. Okay, and you have basically this is min 0 coming and oops, sorry, that's not what I want to do. So first of all, I need to show the decoder here. So this is A1, A0, okay, and the decoder here. See, I have these 0, 1, 2, 3. All right, these are the outputs, and then what I do, I bubble those outputs, right? Because I want max terms. So and then I pull those max term 0, max term 2 into my NAND gate. And the way I implement NAND gate, this is here 1, 2. Yeah, I think I can do better than this. Okay. Okay. And this is my NMOS, pseudo NMOS, and this is an inverter, and this is my Y5. This is exactly what I have implemented right here. Okay, this is exactly, and the rest Y5, Y4, Y3, Y2, Y1, and Y0. By the way, the functions here are the same as the functions here, but one use NOR implementation and one use NAND implementation. The NOR implementation is sum of min terms. The NAND implementation is product of max terms. Okay, now, so what's the difference between the two? Okay, so notice here the series. Oh, bad for delay. Okay, so NAND gate implementation of max terms is not good. No, it is good. Why it's good? It is good because notice here I use one common ground here. And versus here, look at how many grounds I need here for the NOR implementation. Okay, so what does that mean? Using ground lines in the NOR implementation requires more area. Okay, but using NAND gate uses one common ground gate that saves lots of cell area. So this is smaller area, but at the expense of more delay. And since in consumer products, and especially for flash designs, we are after smaller design, cheaper product. We prefer the smaller area over this is faster. This is faster. Smaller area and slow. We prefer the solution over faster and more area. Okay. So the NAND ROM, because it uses one common ground versus those multiple grounds here, which increases the area, the NAND implementation wins as because it saves area and provides cheaper solution. Okay, I'm going to stop here and continue the discussion of the rest of the lecture in the next part. Thank you.